Log on, tune in, find out. Another good idea from Cambridge.
It's 12 o'clock now, so let's finish this afternoon with a talk by Ines Pacharoni. She's talking about matrix orthogonal polynomials and group representations.
I would like to start by thanks to the organizer to give me the opportunity to be here. Very nice place, and also to give this talk, this nice conference. This is a joint work with Juan Tirao, also from the University of Córdoba in Argentina. Let me start with some introduction. It is well known that the theory of harmonic analysis and homogeneous spaces is closely related with the theory of special functions. This is apparent for the case of the two-dimensional sphere, S2, where the spherical functions are harmonic, are related with the Legendre polynomials. Also, in the case of the n-dimensional sphere, the spherical functions are given in terms of Jacobi polynomials. These Jacobi polynomials with this parameter alpha is given by this formula. And it is very well known that Jacobi polynomials are eigenfunction of a differential operator in the variable theta, and also satisfies a three-term recursion relation on the other variable m. This interplay between spherical functions, special functions, orthogonal polynomials, and hypergeometric functions are also present in the case of matrix value setting. And this is the aim of this talk, try to convince you that this is also present in this matrix case. So I will start with the matrix value orthogonal polynomials. This theory was initially started by Crane. We start with the matrix, a weight matrix functions W. This is a matrix L times L, supported in the real line. By the weight matrix, we mean a positive definite matrix functions with all finite moments. If you start with this kind of weight matrix, then there exists a sequence Pn of matrix orthogonal polynomials, orthogonal with respect to this bilinear sesquilinear form. This is a matrix one. It's kind of an inner product, but it's in a matrix. The sequence satisfies that of degree of Pn is n, and the leading coefficient of the matrix Pn is a non-singular matrix. Also, for following the normal arguments, standard arguments, you can obtain a three-term recursion relation for this sequence of polynomials, where here this matrix A is a non-singular matrix. But we are interested in polynomials satisfying also a matrix differential equation of this type. Here, this T here is the transpose of the matrix, and you need to put the transpose there because we have two operators, this differential one, operator D, and this one. This is a recursive difference operator acting in the same Pn, but they are matrices and they don't commute. The coefficient matrices. If you like that this operator commutes, you need to have one of them acting on the left and the other one acting on the right. This is we put in this way, but this is acting on the left if you take the transpose. The differential operators we are interested in are of this special form, where here the function A2 is a polynomial on the variable x of degree at most 2, A1 is a polynomial of degree at most 1, and A0 is a constant matrix. All the coefficients are matrices. An observation is that if you have a symmetric operator with respect to this inner product, to this function, you automatically you have that the sequence Pn is an eigenfunction of D. This is not difficult to see. This problem was initially considered by Antonio Duran in 1997, but no trivial explicit examples were known until this paper, also in collaboration with Alberto Grunbaum, appeared in this year. And these examples were obtained from the matrix spherical functions associated to the complex projective plane, this complex projective plane. At this moment, there are a lot of new examples of this kind of matrix polynomial, orthogonal polynomials satisfying a differential equation. And I would like to convince you that the matrix spherical function is a natural place where you can find this kind of polynomials. So let me start with the definition of a spherical function on a Lie group. We only consider here this matrix group. K is a subgroup of G, and the quotient is the complex projective space Pn. And if you start with delta, a representation of K, an irreducible representation of K is compact. Both of these groups are compact groups. And we say that a function on G taking values in some vector space, finite dimensional vector space, is a continuous function. It's a spherical function of type delta if it satisfies this integral equation. Here appears some scalar function. It's a character. This is the character of the representation times the dimension of the representation. The character of the representation is the trace of the representation. And we also have to require that this condition, that in the identity of the group G, we have the identity transformation in this linear transformation. It's easy to see that if you restrict the function phi to the subgroup K, you obtain a representation of K, multiplicative function, such that it's not any representation, but it has the property that it decomposes as an irreducible function, a representation as a direct sum of K representation of all the same time delta. So we start with an irreducible representation of K in the class delta, and we have this characterization of the spherical functions. The B pi is the space of the representation. A spherical function of type delta could be seen as an analytic function with satisfy these two conditions. This is a kind of how to do this transformation. K1 and K2 is in the subgroup K, G any element of the group G. And the spherical function is an eigenfunctions of all differential operators on G, which are left and right invariant under G. This is the algebra of differential operators. In this case, for this group, this is a polynomial algebra in n independent generators. One of them can be taken as a Casimir operator in G. So for us, the spherical function is an simultaneous eigenfunction of all these operators. If you take the trivial representation, if pi is 1, we have the zonal spherical functions, which are scalar functions, because here we have the complex numbers. And this is a very well-known theory about spherical function. But we work with more general representation of K. The reducible spherical function of the same type delta are orthogonal with respect to this inner product, the trace. This is the adjoint transpose of the matrices. And the Casimir operator is a symmetric operator, satisfying this condition. So matrix spherical functions are naturally eigenfunction of some symmetric operator in the group G. So if we start with a spherical function of some type p, pi, we associate to it a function h. We have to twist a little bit the original function with an explicit auxiliary function, phi pi, defined on this open dense set of G. Those elements whose this coordinate is non-zero. We take this function very explicit, and the important property that it has is this. It has this property. Also in the identity is the identity. So the function, this function A satisfies these properties. All of this. In the identity is the identity. But here we have this important property that allow us to think the function h as a function in the quotient G over K. The projection of this set A in the quotient is this complex space, this affine complex space in the projective space. With this is the affine subspace with all these elements have a non-zero element in the last coordinate. So we start with a function in the group G, and we obtain a function in the quotient. We are in Cn, and the property 3 tells us that the function h is determined by this restriction to a cross-section of the k orbits in Cn. The k orbits in Cn are the spheres of radio r. We introduce some change of variable. For me, the variable is u, this quotient, but it's just a change of variable. Yeah. Yes. So let me say something about the irreducible representation of K. They are parameterized by the n tuple of integers with this property. The trivial representation of K corresponds to take all these number zeros. In general, if you take all these numbers equal to each other, we have a one-dimensional representation. But in general, it's not the case. Our set of index will be this one, omega, when you take n-1 tuples with this condition. Is all the numbers that you can, for example, the first coordinate, if the numbers that you can put in between. It's not so difficult to see that the function h introduced before is a diagonal matrix in some basis, in some convenient basis. This is the Gelfand settling basis. So we can think this function, this matrix function, as a vector because it's a diagonal one. So we have a function h, put it as in a vector. And the fact that the spherical function is an eigenfunction of the Casimir operators give us that this function h is an eigenfunction of some matrix differential operator that we compute explicitly. Here, this is our matrices A and B's, explicit matrices. Both of them are diagonals, but these are not diagonals. So we have a coupled system of differential equations, and we have to try to find the eigenfunction of this system. Naturally, coming also from the spherical function, this operator D is symmetric with respect to some diagonal matrix weight functions of this form. This is some numbers and explicitly compute, and here appear the elements and the set entries. We also can prove that the function h is a polynomial function. So we are here from the set of irreducible spherical functions of type delta. We naturally obtain a set of polynomial functions which are orthogonal with respect to some matrix wave function and eigenfunction of some differential symmetric differential operator. Let me say how many of these functions we have. All the irreducible spherical functions of the fixed K type are parameterized by a pair of W is a non-negative integer, and R is an element on this set omega that we introduced before. We denote HWR, that's the function H associated to it, to this data. All of them are vectors, all these functions are vectors, and we package some of them in a matrix. We take the matrix HW, a matrix whose rows are given by these vectors, some kind of package of a spherical function. Each row is a spherical function. So we obtain a L times L matrix. L is the cardinal of this set. There. And now we have a sequence of matrix polynomial functions taking values in matrices L times L, which satisfies a differential equation, and they are orthogonal with respect to some matrix wave function W, and also they satisfy a three-term recursion relation. It is not a trivial fact, but it's also obtained from the representation theory, tensor in certain representation of the group G. But nevertheless, it's not in the context of matrix orthogonal polynomials, because the form of our operator D. Our operator D is of this form, but we need operators having here a constant matrix, and we don't have. Remember. So to put these examples in the framework of matrix orthogonal polynomial, we need to conjugate the operator by the no-constant function. Then we look for a function, matrix value functions, such that the conjugate operator d tilde be of this form, has the right form. The existence of such psi function is very complicated, but we can look for explicit one, this function. And also, it's a standard fact that if you conjugate the operator in this way, the weight function is also conjugated in this way. And so after this conjugation, we obtain this operator. This is a matrix hypergeometric operator, and it leads to naturally to consider the matrix valued hypergeometric equation studied by Tirao several years ago. We start with a vector space and A, B, and C, linear transformation on it, and we can consider this equation, which is a generalization of the well-known hypergeometric equation in the scalar case. We define this function f(1) in this way, where these coefficients are defined inductively in this way. Start with identity and take this definition. Of course, you have to assume that the eigenvalues are not here, because you need to invert these matrices. this is an analytic function on the unit circle with values there. And if you take an element in the vector space, you get a solution of the hypergeometric equation with this initial condition. And moreover, any solutions is of this form. So we have a description of all solution of this equation near of 0. So our operator is of this form. This is our explicit matrices. And by putting in this way A and B, we have the solution of this equation. Solution are these functions. So the conclusion is that if we take the matrix whose rows are these functions, here are the spherical functions, vector value function, times these functions, we get this matrix, and all these matrices are a sequence of matrix orthogonal polynomial with respect to this way. They satisfy a differential equation and also a 3-term recursion relation. This is a sequence of matrix orthogonal polynomial. And we can give explicitly the differential operator and the 3-term recursion relation. And also we obtain that the function h associated with the irreducible spherical function are given in terms of matrix hypergeometric function, as in the several of the classical case, for some f naught. Let me finish. In the case of you have these representations that I call one-step representations, the block 3 diagonal matrix associated with the 3-term recursion relation is an stochastic matrix. It means that the coefficients of this matrix are non-negative, and the sum in each row is equal to 1. And this was used by Grunbaum to model some quasi-birth and death processes related with the stochastic processes. So I think that's all.
Any questions or remarks?
Yes.
Can you do this also for some of the other examples, like SON?
This one? I think so, but we don't prove it yet. But I think that it should be valid for any representation of K.
But yeah. So, and what about if G is non-compact but K is still compact?
What about with the?
Can you still calculate these functions explicitly?
Yes, only in the case of on the plane of n equal 2. But probably you can. We only did these calculations. We also can compute explicitly. This is a part of this work was done with Paulo Roman also for the non-compact case. SU21. Yes.
I was trying to understand the geometry. I don't think I do, but at some point you had Pn.
Yes.
But that seemed like an artificial normalization, a choice of the last entry of the matrix being equal to 1. So can you cover Pn by patches?
Yes.
By making other
Yeah,
choices?
in fact, there is a lot of things that I couldn't say, but you start with the function, your function is defined in this complex affine plane space. But after that, you have to extend to all the complex projective space. You have to consider the line in the infinity.
Yes.
But it is possible to. Yeah, we do that. Yeah, thank you.
Any more questions or remarks? If not, let's thank the speakers for this morning.
Thank you.